we're going to start with the first plenary session. I'm going to present and introduce to you Professor Steuer. Ralph Steuer is the Charles S. Stanford Senior Chair of Business in the Department of Finance of the Terry College of Business at the University of Georgia. He received a Bachelor of Science from Brown University, an MBA from Cornell University, and a PhD in Business Administration from the University of North Carolina. Dr. Steuer is the author of Multiple Criteria Optimization, Theory, Computation, and Application, the AD-based Multiple Objective Linear Programming Package, and over 100 research articles. Dr. Steuer's research interests are in multiple attribute portfolio theory, efficient sets and surfaces, multiple objective programming, and multiple criteria decision making. A recipient of the Lamar Dodd Award for Creative Research in the Sciences from the University of Georgia, and a Distinguished Alumnus Award from the University of North Carolina. Dr. Steuer was a co-founder and has served as president of the International Society on Multiple Criteria Decision Making, a society that now has over 2,000 members in over 100 countries. In addition, Dr. Steuer has been advisor to universities in emerging countries on the establishment of curricula in management and has been Honorary Dean of the School of Industrial Management at the Ho Chi Minh City University of Technology in Vietnam since 1991. Prior to joining the University of Georgia, Dr. Steuer was a visiting associate professor at Princeton University and on the faculty of the University of Kentucky. So, please receive with a warm applause to Ralph Steuer.
Okay. Thank you very much. And now I'll start the paper here. You know, there are no authors. I did not list any authors here because this is sort of like joint work that I've been doing over the years with a number of people. And that would include Max Wimmer, who's here at the conference. Sebastian Utz is another one from Germany. Marcus Hirschberger from Germany. And then a former doctoral student of mine, York Chi, who's from China. And so it's a sort of a combination of the work that we've been dealing with over the last few years. I changed the title a little bit and thinking about this in the days coming up to the conference here, and to talk about, to phrase it this way, Markowitz portfolio selection, which everyone is familiar with, and then with a third criterion, you know, because it's very difficult to add a third criterion. And I'll try to point that out as we go through. I think I take this off. And all right, I have a lot of graphs. And so maybe not so much in the beginning here, but let's see. Okay, so if we're going to talk about generalizing exactly Markowitz portfolio selection, we need to agree on what Markowitz portfolio selection is. So we have N approved securities. And N can be anything from 10 to 20 to, say, 1,000 or 2,000 securities, depending upon the organization that would be interested in such a problem. So N can possibly get up into the thousands. And so the decision is, well, how much to invest in each? See, most of the securities are going to have nothing invested in them. So the question is, which ones do I invest in and how much? Okay, now traditional Markowitz portfolio selection, there's really two criteria there. You want to maximize your portfolio return while at the same time minimizing risk. So, you know, this goes back over 60 years. So when Markowitz came up with this material, in the early 1950s, he was thinking multiple criteria. I mean, long before, it was sort of like 10 or 15 years before the field of multiple criteria decision-making began to recognize itself as an area of study. And now, Markowitz portfolio selection then goes and calculates the efficient frontier. I'm going to call it the non-dominated frontier, but when you're reading the financial literature, they call it the efficient frontier. And then the efficient frontier is going to be a curve like this. And this is very nice curve because it makes clear that if you want to minimize risk, which we measure by variance, you're going to have a low expected return. And if you want to go after a high expected return, you're going to have to take on risk. So it's a very, and now for those of us in multiple objective programming, you say, why is the curve going this way? Why doesn't it go that way? Well, the thing is, we're trying to minimize this criterion, but maximize this one. So that's why the curve has that particular shape. And the idea of Markowitz was, you know, figure out your securities, formulate this program so that you can compute this curve, and then look at the whole curve, the entire curve, and visually figure out where you want to be. What are your trade-offs between risk and return? So maybe if there's someone who's approaching retirement, they might want to be at this part of the curve. And if you're a young person willing to take on some risk, maybe you're up here. Maybe most people at midlife are in here. So it shows all those different possibilities. So what it is, since not everyone has to have the same optimal solution, the individual decision maker would look at that curve and decide where they want to be. So now this curve in multiple criteria terms is in outcome space.
Right. Now, here we have something that's really not necessary. I just do a simple definition of what non-dominated means. And then also, in contrast, I'm going to use the word efficient. But non-dominated is going to pertain to points in outcome space. And their inverse images in decision space I'm going to use the term efficient. So non-dominated means outcome space, efficient means decision space. Okay, I'll do that throughout. So now in finance, at least in certain areas of finance, it's important to see the whole non-dominated frontier when trying to make a decision. And why is that? Well, there are two reasons. One is, it's nice that the non-dominated set shows all candidates for optimality. But there's another reason, and that is, many times in finance, a person will not agree to a solution being optimal unless they can see and be convinced that everything else is worse. Because most of the time in finance, if you go to a person and say, here's your optimal solution in the absolute, they'll say, I don't like it. I need more return and less risk. And somehow you have to get them to come to the conclusion that their optimal solution doesn't have more return for less risk. So one way to do it, and this works nicely in the bi-criterion Markowitz case, you can see why you're picking a point because you can see why everything else is worse. So that's why I'm pursuing in this the generalization of Markowitz in the sense of showing the total frontier. Okay, now this is the Markowitz mean variance portfolio selection formulation. And actually, it's really a bi-criterion linear programming problem, except that one of the objectives is quadratic. It's and a lot of us in multiple criteria optimization, sometimes we don't even think that bi-criterion is multiple criterion, because most of the times bi-criterion problems can be solved pretty quickly with single criterion techniques. But when you go to 3 criteria or more, single criterion techniques won't help you solve that problem by much. So, but the point I'm going to make here is that this is kind of an, other than for the fact that one of the objectives is quadratic, everything else is linear. And actually, being a quadratic objective, that's about the nonlinear objective that is closest to being being linear, because all the first derivatives are linear. So, and if we look at this, here's the feasible region. Hey, this is just a normal type of linear programming feasible region. There's nothing unusual here. It will typically have one equality constraint. And then it'll have some less than or equal to constraints, like you can't invest more than 30% of the portfolio in oil or something like that. And there'll be a handful of those. There won't be too many of them. 5, 6, 7, not too many. And the other thing is here, but there will be an upper bound on each security. See, so the X is the vector of securities, and there'll be an upper bound. Like you can't invest more than 6% in this security. You can't invest more than 3% in that security. But this is pretty standard, ordinary linear programming. So the basic problem, even though when we start working on it, you sort of lose the sense that it is such a simple problem. All we're doing is it's a 2-objective linear programming problem, except that this objective is quadratic. All right. Now the quadratic, being quadratic, it needs a covariance matrix. So that's going to be n by n. So if you're dealing with 30 securities, it's a 30 by 30 covariance matrix. If you're dealing with 1,000 securities, it's a 1,000 by 1,000 covariance matrix. You usually get your covariance matrix from historical price data. Okay. The individual components of this X vector, they're just the amount that you're going to invest in each security. And most of the time, if you said you had 100 securities, 100 approved securities that are eligible for investment, chances are most portfolio selection solutions would say that invest nothing in maybe 60 of them, and then only in the remaining 40 do you actually invest. So most of the X values in our solutions will be zeros. Okay, this is just a symbol for the expected return of each security. So the covariance matrix and the expected return vector, you generally get that from historical data. You might look at historical data and then tweak it a little bit. And here, I'm just emphasizing this point. It's just a 2-objective, multiple-objective linear program in which one objective is quadratic. All right. Now, a little bit about how do we get the data to parameterize the model. Now, this is using historical. This is just to suggest how historical data is used. And so, how do you get the covariance matrix? Okay. Let's say we're looking at 3 stocks, and we look at them for 60 periods. A typical period is 1 month. Shorter periods tend to have more noise in them. So the typical period for collecting historical data is 1 month. Sometimes people will try 1 week and so forth, but most people settle on 1 month. So this would be 5 years. So you look back over the last 5 years, and you study the price data. You'd say, well, why not go back 10 years? Well, 10 years ago, it might be a different world than today. Okay, so we're better off staying with the upfront data here. So this stock in the first period gained 1%. This stock in stock 2 in the last period lost 2%. Okay. Then we get our covariance matrix, and it has numbers in it like this. They're small numbers, okay? And there's something else that comes up. I won't have a chance to get into in this, but it can often make a difference whether this matrix here has full rank or not. If it has full rank, then we're in great shape, okay? But on bigger problems, it almost always will not be a full rank. And we just have to realize that's life. See, if it's full rank, it'll be positive, definite, and that's going to make everything simple. But, okay. A little bit about how we calculate variance in the form of this mathematical expression. So this is the vector of weights, how much we're investing in each security. This is the covariance matrix in this. So if we decide to put 50% of our money in security 1, 30% in security 2, 20% in security 3, and I would like to figure out what is the risk of this portfolio in terms of variance. I will just do this matrix calculation. X transpose, sigma, X. And that will give me a figure, that gives me a result like this. Now, most of the time when we show non-dominated, the efficient frontier or non-dominated frontier to the decision maker, we have on the vertical axis expected return. But on the horizontal axis, we generally have standard deviation and not variance. You know, Markowitz mean variance model, but when we show results to the decision maker, it's really like mean standard deviation. And the reason for it is you can't make sense out of this variance number. It's some small number per month squared. And what does that mean? See, we know, of course, the bigger the number, the more the risk. The smaller the number, the less the risk. But what a particular number means is really hard to decipher. So that's why people go with standard deviation rather than variance. You just take the square root. Now everything becomes simple. You take the square root, and it turns out, in this case, to be 1.82% per month. Everyone who's had a little bit of statistics can identify, can understand physically what that means. But trying to understand this physically, I don't think there are many people who are able to do that. So in our graphs, we're going to be showing most of the time standard deviation on the horizontal axis, because that's the way it has to be shown to a decision maker. All right. Now, this is a graph of a very simple portfolio problem. Say this one would have just 3 securities in it. All right. And beta, that's the upper bound on each security. So this in this case, in this case, because it's a small problem, you can't put more than 80% of your portfolio in any security. And since if you were to go back a couple slides, there was that one equality constraint, and what that is that means the feasible region of the portfolio problem has to be some subset of the unit hyperplane. You know, the fact that all x's have to add to 1. That's a hyperplane. We're calling that the unit hyperplane. And the other constraints, ax less than b, they just chip away at the unit hyperplane. So in this case, here's your unit hyperplane in the non-negative orthont, and this beta clips off these corners. And if there are some other ax less than b constraints, it might take a little bit more off. Okay, and this is the image. Z is the image of S in outcome space, and here I've already taken into account with standard deviation. Okay, and it's going to be a shape like this. The backside has this kind of peculiar scalloped effect. I sort of think of it almost like an umbrella on its side. We generally don't operate here. We operate on the non-dominated frontier. See that part of it. Okay, so we have 2 spaces here. We have decision space and criterion space, as we would normally expect in a multiple objective problem. All right, now what we have here is I should have a line here. For some reason or other it's missing. There should be the non-dominated frontier is this curve. And that curve comes from these line segments here in decision space. So these are the efficient portfolios, and these are their non-dominated expected return risk points. Okay. Now, it looks a little peculiar here, but you know, probably many of you have heard that the non-dominated frontier is piecewise hyperbolic, and the efficient portfolios are piecewise linear. See, because this straight line here, when run through the objectives, because of that quadratic objective, that turns itself into a hyperbola. See? So this particular curve here, it looks like one curve, but it's made out of the image of this straight line, the image of this straight line, the image of this straight, and they sort of all blend together in most cases in a continuously differentiable fashion. Okay, so even though this one has corners on it, this one has corners on it, this one has, they blend into each other. All right. So now, how do we calculate this? And so we calculate the non-dominated frontier, that whole curve, by solving this parametric quadratic programming problem. Markowitz proposed a method like this in 1956. It's a very difficult to understand method, but in essence, it's a parametric quadratic programming problem. So, and it has, here it is, the feasible region. There's the unit hyperplane. These are some extra constraints that chip away at that unit hyperplane. Okay. Now what we have to do is we have to solve, it's a quadratic programming problem because of this quadratic term. And it's parametric quadratic because I have to take this parameter and solve this problem for all different values of lambda 2 being greater than 0. Now you might at this point say, well, why does that have a subscript of 2? Because I'm thinking of this objective as being the second objective. See, later there'll be a third objective. This is the first objective, this is the second objective. So the weight here is really 1. So this, I have to solve this problem for all different values of lambda 2 greater than 0. And when I have that done, I'll have the whole curve. Okay? And the curve that I'll get consists of a number of number of different hyperbolic segments, but they blend into each other so smoothly it looks like it's just one curve. Okay. Now, okay, here to do a little example. This is an example. This is actually a problem that a randomly generated portfolio selection problem that has 10 securities, and the resulting non-dominated frontier turned out to have 8 hyperbolic segments, which is kind of a typical number with 10. Sometimes it could be 7, sometimes it could be 10, but it has 8. So I have just indicated with dots where one hyperbolic segment ends and another one begins. See, so there's 1, 2, 3, 4, 5, a little one here, 6, 7, 8 hyperbolic segments. And these are the place where one joins the other. Like I say, they blend into each other in most cases in a very smooth fashion. There can be kinks, but they're rare. So, and once again, standard deviation on the horizontal. Now, how do I get that curve? The way I solve the parametric quadratic programming problem is to do it by means of the Kuhn-Tucker conditions. All right. So we can recognize. So this is the Kuhn-Tucker system of linear equations. for the portfolio problem. It's still originally this bi-objective problem, but see, you will recognize them. Here's the covariance matrix. Here's the one from that constraint that says all x's have to add to 1. Okay, there's the A matrix, you know, no more than 30% in oil and so forth. And if I follow the rules and do it using the Kuhn-Tucker conditions, this is what I wind up with. There's that parameter. I have to vary this parameter from 0 to plus infinity. Okay. Then there are some other restrictions here on the individual variables. But this is the Kuhn-Tucker system for that problem. Okay. Now what it is, I have to solve this system, find out all solutions to this system for all different values of lambda 2, 0 to infinity. It's best to start from plus infinity and go down to 0 rather than the other way. So I started at infinity here. And then what's going to happen here is this is a linear system. So I can make changes in this system, and if I make the changes too much in this linear system, something's going to go infeasible. And at that point, I'm going to have to pivot. See? So that's the scheme here. I'm going to start here with lambda plus infinity. And then I'm going to start lowering it from plus infinity, you know, to 10,000, to 9,000. And as I'm changing the right-hand side here, these variables over here are changing. And as long as I don't run into any of these limits, I can keep lowering lambda 2. But quite quickly, I'm going to really run into a limit. And that's going to give me the first lambda 2 range. And each range of lambda 2 is going to give me a hyperbolic segment. Okay? So coming down from plus infinity, determine the range over which lambda 2 can vary without having the system go infeasible. In other words, without forcing a pivot. And so what it is, I've got to decompose lambda 2 from 0 to plus infinity. Well, I've just now gotten the first segment here. See, this is my first lambda 2 piece. Then I'm going to work on getting the next segment. Then I'll work on getting the next segment. When I get down here, I'm done. I have the old non-dominated frontier. But this is so it's a repetitive process here. So I'll just do it one more time. See, so this is what I get. I can extract. See, so this is when lambda 2 is infinity, and this is when it hits its first point coming down the curve. And I can extract out of that tableau information that gives me this hyperbola, but it's only this portion of the hyperbola that I use. See, lambda 2 tells me this point, and lambda 2 tells me this point. So now I just do this repetitively, and I construct these different segments as I come down the curve. So I'll go through the routine one more time. But so what I do then is I do my pivot. See, I lowered lambda 2, say, down to 9,000 or something, and I can't go anymore. So to go further, I have to pivot. So I do my pivot. Now I have a different system here. I mean, it's the same structure, but things have changed a little bit. Some of the numbers have changed in here, but it's still the Kuhn-Tucker system. And then I take lambda 2 and I say, okay, I was at 9,000 at the limit before, but because I pivoted, now I can go down maybe to, 1,000. And so after pivoting, I get this. Then I take lambda 2 and I say, how much further can I reduce lambda 2 without now going infeasible, or in other words, without forcing a pivot? And that enabled me to determine this second segment. So I've done 2, and in this problem, if I do this 6 more times, I'll get down here and I'll be done. I'll do the whole non-dominated frontier. Okay, so that's the routine. And so there's the picture with the second hyperbola, and I extract, this second right segment off of that, and it's, when I do the next one, there'll be another hyperbola there, and I'll just pick off this part here. So that's the way it goes. So now there's something else about there is a significance to these different hyperbolic segments, because say I'm in this segment. See, the securities that are in the portfolio at a positive level stay the same in this segment here. They will change proportions, but they stay the same. Now what happens if I go to this segment that's not shown? Well, what happens here is I'm going to probably kick out one of the securities that's in the portfolio and bring in something different. See? So that's what these different segments tell me. Each segment involves the same securities, just in different proportions. But if I go from one segment to another, then I'm kicking something out and bringing something else in. That's done. That's what the pivot does. It figures out what's to go out and what new is to come in. All right. So so that's the routine. And all right. Now computer times. With a regular Markowitz portfolio problem now can be solved quite quickly. Here's a problem with this many securities, 1,000, 2,000, or 3,000 securities. And if I say that no more than 4% of the whole portfolio can be in any one security, and run it, I'll wind up with a frontier here of over 200 of these hyperbolic segments. That number grows slowly when the number of securities grows pretty rapidly. Computer time, I have a pretty fast computer, so it doesn't really take too much time. 2.1 seconds to do all this Kuhn-Tucker system and a business and so forth. So I use the term QL here because one objective is quadratic and one is linear. All right? So that is the end of part 1. Now I go to part 2. So that tells us exactly what Markowitz portfolio selection is. Now the idea is how to go to 3 objectives. Okay. Now we're done with 2 objectives. Now, if we introduce a 3rd criterion, the question is, well, how much complexity are we really going to bring into this? So if we introduce a 3rd criterion, we really have a 3-objective, multiple objective linear programming problem, but 2 objectives are quadratic. Same feasible region, same normal type of feasible region. About the only thing that's unusual about the feasible region is that this feasible region is that it has, it'll have always one equality constraint and then generally a handful of inequality constraints. So but it has a lot of variables because it'll have a variable for each security. So it's a feasible region that has a small number of constraints and a large number of variables. Right? Because there has to be a variable for each security. So, but still, it's kind of a normal feasible region. All right. So, no, this is not the right point here. Sorry, I'm giving it away here. Ah, there I am. I was trying to explain the last slide. All right, this is the second part. And the reason I have two parts is because the parts involve graphs, and I haven't figured out a way to mix the two different types of graphs in the same LaTeX document. There is a way. I understand there is a way. I just haven't implemented it yet. But all right. So this is the second part. With the third criterion, what difficulties are we going to face? All right. Here, this is what I should have been talking about. Forget what I said there for a minute. Here is the problem with the third criterion. The third criterion comes in as linear. You can't be any simpler than that. Okay. And so what I'll motivate the third criterion as sustainability, social responsibility, that type of thing. So we have the same two original risk-return objectives, and we had a third one. Same feasible regions. Feasible region doesn't change. So this is just kind of the... Okay. So an additional linear criterion. And now the solution to this tri-criterion problem isn't a non-dominated frontier, it's a non-dominated surface. And since Markowitz calculated the non-dominated frontier, I'm going to try to calculate the non-dominated surface. I'm going to try to do everything that Markowitz did with two criteria in three criteria. So, once again, I stress this point. It's just a three-objective MOLP, just that one of the objectives is quadratic. So that's all a portfolio problem is. Okay. Now, how do I solve that one? I solve for the non-dominated surface in a fashion that's very similar to how I solved piece by piece the non-dominated frontier. So this is the formulation. Feasible region still the same. First objective is here. The second objective is expected return with its lambda 2 parameter. Now the third objective comes in here, sustainability, and it's got its own parameter. So I have two parameters now. And what I want to do is solve this multi-parametric quadratic programming problem for all solutions with lambda 2, lambda 3 greater than 0. So this is like a little two-dimensional non-negative orthont here. So instead of decomposing a straight line with bi-criterion portfolios, I've got to decompose a non-negative orthont here. Now the surface of this problem consists of hyperboloidic platelets. They're like the back of a turtle. They're plates and they have this hyperboloidic curvature to them. So, and here actually it's clear now that we're trying to solve this problem, and we're going to have to wrestle with three different spaces at the same time. Decision space, of course. Criterion space, of course. And then there's parameter space, the space of these things. So I just have to keep that in mind. Okay? So that's the problem. And then how do I solve that problem? It looks almost exactly the same as before. I take the two Kuhn-Tucker conditions of that problem, and it's exactly the same here. You know, there's the one for all variables must be added to 1 in the A constraints. The only thing that's different is now there's a third problem here, a third thing here. So what I've got to do is I've got to solve this system of linear equations for all solutions that may have different values of lambda 2 and lambda 3. Those lambda 2 and lambda 3 have to be positive. Okay. So I determine a first polyhedron over which lambda 2 and lambda 3 are both positive. And then I try to vary those lambda 2 and lambda 3. So there's play in this system. So I'm trying to figure out how much can I jiggle those lambda 2 and lambda 3 and not go infeasible over here. there's going to be some slack in the system, and I can do that. But if I do too much, I will make something go infeasible over here. So I can't do that. If I want to go beyond, so if I want to go to the limit of feasibility and then go over the limit, I have to pivot. See, but I'm trying to figure out how much can I change these without having to pivot. And maybe I find out, here's my non-negative orthon, lambda 2 and lambda 3. And this is, over this region, I can pick lambda 2 and lambda 3 values and change them, and I don't have to pivot. But if I change them too much, I have to pivot. See, I'll have to cross this line. So in changing this, I'm going to have to eventually, see, I have to decompose, just like I decomposed that straight line, I have to decompose this whole non-negative orthon into little polyhedron. So I'm going to eventually have to cross this line, see what's over here, cross this line, see what's over here, and cross this little straight line, see what's over here. So I now can see that I have to go to 3 places, but I can only go to one at a time. So I pick one of them, and I put the other 2 in the list, and I'll say I'll get to you later. Okay. All right. So what it is that polyhedron pertains to. See, what happens here is that we're not done solving it. We've only solved this, but this is what it's going to be like when we're done. Okay, so that polyhedron from the previous slide will give me this particular platelet of the non-dominated surface, because the non-dominated surface is made up of a bunch of individual platelets, and I've calculated one of them, just like I calculated an individual hyperbolic segment of the two-dimensional non-dominated frontier. This is the first hyperboloidic segment that I'm computing. All right. So, okay, that's one. So I've got to see, because I've got to cross this boundary to figure out what platelet's over here, and I have to cross this boundary to figure out what platelet's over here, and then actually I have to go around the corner here and figure out what platelet's over there. See, those are the 3 places I have to go to, but I can only go to one of them at a time. But I put the others in the list, and I'll get to them eventually. All right. So now I want to figure out another platelet. So it's the same routine. Here's the Kuhn-Tucker conditions again. And now, since I've pivoted, see, the numbers are slightly different over here on this side. And then, now that I pivot, I'm now trying to figure out, now, how much can I change lambda 2 and lambda 3 and still stay feasible over here? And so I extract that information out of these Kuhn-Tucker conditions. And, okay, so so I pivoted, and so I'm done with the first decomposition. I've pivoted. Now I try to work on another decomposition. And let's say that I had to cross this line, I had to cross this line, I had to cross it. I picked this one randomly to be the first one. I'll get to these later on, see? And that brought in this new region here. So eventually, if I keep doing, eventually I'm going to have to go here and here and here, see? So, but eventually I'll fill in the whole non-negative orthon. And when I fill in the whole non-negative orthon, that's when I know I'm done. So, okay. So that's the second lambda 2, lambda 3 polyhedron. And that gives me this second platelet. See, so by doing this repetitively, and that's the routine. I just keep doing that and doing that and doing it. One by one, I keep adding platelets until I'm done. So that's it. So that's what I'm saying here. Okay, we've processed the second Kuhn-Tucker condition, so now I have to process the third Kuhn-Tucker system to get another platelet, and so forth. Okay. So now, if I'm done, I will have this whole surface. See, eventually I've got the whole surface. Now we're starting to see some complexity here. Before, when Markowitz calculated his two-dimensional frontier, you know, anybody can look at it and understand it. But now we're looking at a surface, and what we're supposed to do here, in the Markowitz sense, okay, there's your, instead of non-dominated frontier, it's your non-dominated surface, and somewhere on that non-dominated surface is your optimal point. Look at it and pick it. Well, that's not easier said than done. You know, it's not easy to look at it, you know, and say that, and figure out which point it is. You know, different angles, it looks differently. So what's happening here is that, you know, if visually selecting a best point on a surface is not easy. Visually selecting a best point on a curve, no problem. But when it becomes a surface, so this is what's happening. So maybe we need some cognitive tools to help us in the process to figure out where it is, because somewhere out here is our optimal solution, but how do we know it? See, so maybe we should think of doing some cognitive types of things to help us understand the surface better, and then maybe we will be able to narrow it. So part of the point of this lecture is to show how difficult decision-making becomes when going just from 2 objectives to 3 objectives. It's like there's a quantum leap in difficulty. You know, if you have a single objective problem, no difficulty. A bi-objective problem, oh, it's a little more complicated, but it doesn't seem. But you go to that third objective, and there's a tremendous jump in difficulty. So, okay. So, what are some of these cognitive things that we can do? Well, this is a typical one. If you can show the decision maker the minimum and maximum of each criterion value, that helps the decision maker understand, you know, the size of the problem. That's no problem here, since I'm calculating the whole non-dominated set. It's easy for me to extract from that information the minimum and max over the feasible region. If you don't calculate the whole thing, oftentimes you can have trouble with the nadir bound. You know. But this is no problem here because I'm calculating the whole set. So that's one cognitive thing that people have been doing that's not new with this research. So, all right, what else can we do? I can maybe help the decision maker understand that surface by putting in contours. So each of these curves here has the same standard deviation value. Contours of constant. So this has a standard deviation, this has a larger standard deviation. All these things here have the same standard deviation. Larger, larger, and so forth. So this is where the standard deviation is the greatest. So you get some idea of the curvature of this set, and you can see that these points out here have a high standard deviation, high risk. These would have low risk, but probably very low sustainability and expected return. Okay, that's of some help, you know, and you say, well, if I can do contours of constant standard deviation, I can probably do contours of constant sustainability. So all of these would be, you know, so this if I want, so these are contours of constant sustainability. So this one has a lot of sustainability. It's very good on the sustainability criterion, but probably terrible. I mean, we can see it's terrible on risk, and probably terrible on return too. But still, how many people would be able to pick the best point based upon the information so far. But this is reality. It's not my fault that this problem has a feasible non-dominated surface like that. I mean, this is normal. But so the difficulty in just going to 3 criteria is I think is really difficult. And then, all right, what else can we do? All right, now the problem before is we didn't know what suspension was connected with this. So I could project that this non-dominated surface onto the standard deviation sustainability plane. That might help me understand the solutions on this. And if I can do it on one plane, I could probably do it on another plane. So I take that same non-dominated surface and I project it onto the risk-return plane. See? And it turns out here, this is the bi-objective non-dominated frontier. Now this whole thing is the non-dominated points only because of the 3rd criterion. See, with 2 criteria, this is my non-dominated set. With 3, just add that extra criterion, and this enormous extra area becomes non-dominated. So the question is, where do you want to be? You know, in here. If you want to forget sustainability, well, then you're going to be in this upper boundary. If you want to take sustainability into account, you want to go. All right. So this is helping, but still, it's a difficult problem. See, and I don't really, in the end, I really don't have a solution for the best way to analyze a surface and eyeball the best point on it. So I'll be finishing here in a little bit. We're at a time. Okay. So this would be, say somehow you narrowed it down to a particular platelet for some reason or other. Well, this could be the platelet you're studying. See, and like I say, same securities, just in different proportions here. If you cross over into another platelet, you're throwing out one security and bringing in a replacement for it. But these would be the same securities, just in different proportions as you move. And this is how it would project here and here. Maybe that's helped. So we've got a lot of, and now the other thing is in three-dimensional graphs, rotation. So let's look at the thing from different angles. The tool I use to make these graphs doesn't accommodate rotation, but I'll just do it in steps. So here's what we're going to do is we're going to watch this axis change and actually point right at us. Okay? So it's here, and then I'll change it. It's shifted a little bit, and these things here, and this thing's going to point right at us, so we don't see it. So I rotate it a little bit more, and then I rotate it to the point that this axis is coming at you. Now this probably, of all the graphs, might be the most useful because with the contours in there. Because, oops, there's the Markowitz 2-objective frontier. And now all this, these are non-dominated because of the 3rd criterion. But see with the contours here, as I move this way, I move to higher sustainability. So all these things here have the same sustainability. So maybe projecting onto this 2-dimensional plane, a 3-dimensional surface, might be one of the most useful ways of figuring out that, because see, you could read off this graph the coordinates of this point. You know, certainly it's this much standard deviation, it's this much expected return, and then we'd have to indicate what the sustainability was on that band. So then you could actually play around with this, and maybe this is the one that will help you the most in the end. But all this, we need more help in cognitive tools and in analyzing a surface. All right. Now, another thing we thought to do is to form a cube. And that is, say, for this point, if I create a little rectangle here, I can see right away the coordinates, the 3 coordinates of this point. So we're just trying different things. Okay. Now, putting this on a computer. Okay. So I have a code that can solve this multi-parametric quadratic programming problem. And your ability to solve large problems gets dramatically reduced. See, here are the results from before, 1,000, 2,000, 3,000. There's no way I can calculate a surface with that many securities, see? And the times are really fast. There are a lot of these little individual segments, but when I go over here with just 250 securities, the time is not a problem, but the number of platelets is. So this one has 10,000 tiny little platelets. And what happens here with the code actually begins to choke on the number of platelets. It can't keep this straight. See, time is not a problem, but when I get past 20,000 platelets, the program starts to blow up. Even though time's not a problem, the number of platelets is. So I can get myself up to 750, and I'm still all right, but I can't get up into these figures here at the present time. You know, this is all with a problem where no more than 4% in any security. Okay. Now, if you have a third criterion in portfolio selection, I'll finish here in 2 minutes. That third, see, we talked about the third criterion being linear. Well, it's possible the third criterion could be quadratic. See, then you would have 2 quadratics and 1 linear. Actually, Markowitz himself, who's probably approaching 90, wrote a paper recently where he could see that in portfolio selection that there could be a third criterion and that could be quadratic. And but he, in this little paper that he wrote in the Journal of Portfolio Management, he said no algorithm exists for that. He couldn't figure out an algorithm for it. But now we think that the non-dominated frontier is going to be a surface. And we think the surface of this consists of hyperboloid platelets too. But no one knows how to compute them. So this is a totally open mathematical question. Okay, what are the issues when there's a third criterion for it? It's not easy to pick a point off a surface. Okay, dramatic increase in the amount of choice. You know, the non-dominated surface dramatically increases in size. The simplicity of the bicriterion model gets lost just by going to that third criterion. Yet, many criterion problems exist in reality. You know, where the third criterion could be dividends, it could be liquidity, it could be sustainability, it could be other things. I mean, these problems are there. And as problem size grows, the number of platelets explodes. See, and after 20,000, computationally, we're not able to make it work. Okay. And if the third criterion is quadratic, see, nothing is known about that. We can do work on it when the third criterion is linear, even though we don't have a hard time interpreting the results. But the third criterion, we don't even know how to do the surface. No one knows how to do the surface. So that, ladies and gentlemen, is the end.